Welcome everyone to another lecture. Today we want to talk about data wrangling. So today is about getting data that is in an arbitrary format into a very specific format. So in the last chapter we were focusing on ggplots, and the data was already nicely formatted so that we could focus on learning how to plot things with ggplot. Now, however, we could be looking at arbitrary data sets and learn how to bring them into a format that suits our syntax of ggplot so that we can work with it. Also, often you will have a data set consisting of a lot of variables, but you're not really interested in all of those variables, or you need to combine them somehow, or you need to find a summary of those variables. And so you need to run some computations with that data and all of that. So this number crunching, this is what we usually refer to as data wrangling. In practice, this actually takes a lot of time and effort to do. So this can take more time than what you're actually finding out later on. So you will spend a lot of time just bringing the data into a specific format you want to look at. And to make this task a little bit easier, the tidyverse has a couple of packages, and these packages we want to work with today. Alright, so let's start with a data set. In the lecture notes you will find a link to the Gapminder homepage where you can download the following files, so this non-net users in %. And the data set consists of people who did not use the internet in the last 3 months for any location, and this is calculated as the percentage of a country's total population. And if you download the file and open it, then you may see that it will look like something like this. So I just open it with any arbitrary editor, and you will see this data is just consisting of a bunch of values. You can call it values. I mean, Afghanistan or Albania, it's the word, but in data science speak, it's still a value of a variable. And in any case, all of those values are separated by commas. And this also explains why this file has this extension. It's a comma separated, it consists of comma separated values. And we can easily get the data into R, so let's do that. So if we load the tidyverse, then you will see that here is there's also a reader package which helps us to read CSV files. So with the command read CSV, we can simply give the path to the file location. So in my case, the data is stored within my current working directory, and there within another file called data, another folder called data, and then I can just simply give the name of the file. And as you can see, here's the data now. It's now formatted a bit nicer than with commas. And also you will get a notification how the reader or the read CSV function interprets the values. So here it's, you can see country will consist of character values, and everything else, so the default will be doubles. You can see it here as well. In any case, we can simply save the file, and now we have the variable tip, which will consist of all the data we're looking at. We can look at the first few rows with head tip, or we could also just call it, and then we can scroll through this. As you can see, this is a real data set, so there can be instances where there are missing values, and in any case you see a lot of columns here. Again, let's not, same as last week, I mean, let's not look at every country, let's look at a few specific countries. So let's filter again. I mean, this is nothing new, the filtering stuff. So here, let's look at these specific countries, and then let's look at these. All right, so here we have now all the data with respect to these 5 countries. And what we could think to do is to plot or visualize the evolution of the internet usage quota over time. So on the x-axis I would like to have the time, so the years, and on the y-axis I would like to have the quota, so the percentage. And then I would like to have 5 different colors for these 5 different countries. And as you can see, what happens here is, or not what happens here, there's a problem, at least in our data set. We cannot really plot this. For instance, if we were to try using ggplot, then we would need to give aesthetics for the x-axis. Well, we cannot really give a variable for the x-axis. We need something like year, but there is no column that is called year. So what we see here is that we have all the data we need. I mean, we know these are the years here and these are the percentages we want to get, but we don't have it in a format so for ggplot to work with. So in these kind of instances we need to rearrange the data a bit, and I will shortly explain how that works. For now I will simply copy and paste the code into this to see first what I mean. So here you can see we have arranged all of this data into a new table, which now consists of the of a year column and a percentage column. And now I can actually plot what I wanted to plot. So here I need gmline, and of course I will need this filtered and rearranged table. Of course I will need a color, aesthetic. Now this looks like something, looks like what I wanted to get. I can even add points. And as you can see, we will get a new notification now that there are missing values. That is because, as you can see here, or also here, that there are missing values for Afghanistan. All right, so after rearranging, we were easily able to plot this now. And the reason why we had to arrange this data set is because, well, ggplot needed it to be rearranged, but the whole point of it is that this is a tidy format. So in the tidyverse, a lot of functions or packages work with tidy data. And what is meant with tidy data is that each variable will need to consist of its own column. So for instance, we have 3 variables here, country, year, and percentage. And each observation will have its own row, and each value will have its own cell. Contrary to that, in this case here, it's kind of jumbled up. So this value here corresponds to both variable year and Afghanistan, and also there is no column for the year. And so that we can get our data into the specific format, we need to do something which is called pivoting, which is what I've done here. It's basically rearranging that. And because it sometimes can be hard to understand what these pivot functions do, in the lecture notes you can find an animation, or not exactly in the lecture notes, but on GitHub. There is this animation which kind of retransforms the data. So basically we have it in a wide format and a long format, and with pivot functions, so with the functions pivot longer and pivot wider, we can go back and forth between these two arrangements. So in this case, we did that. So here we used our tibble and we gave it to the function pivot longer. As you can see in the documentation, the first argument is always data, so it works nicely with a pipe. And there we have to say, okay, which columns need to get rearranged. In our original data set, of course, the country column is already in the way it should look. It's a variable and has its own column. But all the other columns need to get rearranged. And therefore we can say, okay, arrange all but the column, the country column, which we can do with this minus here, which means take all but the country column. And then we have to specify, okay, what to do with the values now and what to do with the names here. And as you can see, well, the names, they correspond to our variable year. So we'll just say, okay, just name this new variable year. You could also call it time. Then here this would oh, of course, I need to reload it again. Names to this is the problem. So if we do this, so here we would get time. All right, but in this case I want to stick with year because my code, as you've seen just now, works with that. And so we made sure that the names of the columns will correspond to the new variable year. And the values in here, well, these are the percentages of the internet usage. So I will put them into a variable percentage, and this is why you get this column here. And as you can see here, I have another step, which is the mutate step, which we will also deal with in a few seconds. The main difference that happens here is that if you just run the pivot function, you will see that the year variable corresponds to character values, and this is something ggplot does not work with nicely, so we need to convert it to actually numeric variables. And this is what mutate does. Mutate is the tidyverse functions to change data, basically, or to change columns of a table. And here we just said, okay, the year variable should now just be the same as as before, but now it needs to be converted as a numeric. This is the idea behind the mutate function. And after we've done all of that, it is now in a format we can use. As I said, this feels tedious. I mean, it's just rearranging the data, and I'm talking so long about this now. But this is in fact what is a common task in data science. You will need to spend a significant amount of time on figuring out how to rearrange the data and how to jumble around the data so it does what you need it to do. And in this case, you need it to be in a specific format, so not the x-axis of our plot cannot be or shouldn't be of character, so they should be doubles, and this is why you needed to convert it, and also you needed to rearrange the data. Okay, so the what we use is pivot longer, and basically you can remember it that if you have a lot of columns and the column names actually correspond to a variable, then after rearranging your table or your tibble will have more rows, so it will be narrower and it will be longer. And the opposite of that is to make it wider, and this is why the antagonist to pivot longer is pivot wider. So just for so that you've seen it, we can take our data that is in a tidy format now and make it put it back into the original format. So there you will need to give the arguments, okay, the names from, okay, you might want to make it wider, So you will get a lot of new columns. These need to be names. Where do the names come from? In this case, they came from year. And where do the values come from now? Well, in this case, they came from percentage. And so values from, and there we have we were able to retransform the data back into its original format. Sometimes in this not in this case, but sometimes you will also need to identify the data. So this is why there is this ID calls argument. So if there are more columns, or if you want to rearrange the data, sometimes you will need a unique identifier for the data. And in these kind of instances, you will need to use ID calls. You will need to do that in the exercises. I just want to mention it that in this case we didn't need it to, but in the exercises you will. Okay, so all of this was just to show you how to rearrange data. So basically rearrangement is done via pivoting. So in these cases the two functions pivot wider and pivot longer. Also I've showed you this animation, and here you can see the gather and spread functions. They were the predecessors of the pivot functions. So this is why this is an old animation, but it still works the same. So this is why I'm still showing you that. And now that we can rearrange data, let's transform data. So earlier you have seen that with the mutate function, I've simply transformed the data. So I changed year from character values to double values, and all of that and more can be done with the mutate function. And for that, or for demonstration, I kind of need a new tibble so that we have a little toy example to play with. And so we can first create a new tibble. This can be done with the tibble function. The syntax is pretty straightforward. You just declare variable name. Let's just call it first variable 1. You throw in a couple of values you want to look at. I will just take the ones from the lecture notes, then you put a comma there, and then you declare another variable you want to get. So in this case, I can declare a tibble like this. So let's call that our dummy tibble, which is our toy example we will work with. Alternatively, I mean, as you can see, it's quite easy to declare a tibble like this for small examples. But if you want to have a really small example, in this case, we could have done it differently as well. Because this kind of is a really small example, you can use the function tribble, which is the same as tibble but with an R in it, which probably stands for row-wise. So let's declare the same tibble but row-wise, which means that we will have to declare everything row by row. So in the first row we will have the variable names, which is why we will need to put a tilde there. And then we can simply put the values we want to look at. So this is 100, 2, and 1. So the first values here. Then the second values would be 200, 4, and 1 again. 200, 4, and 1, and so on. I will skip a bit of the work. And this way you get the exact same tibble, but you have it in a more human readable way. So for really small example, it is a good idea to simply use the tribble function. Of course, the tribble function is only really useful if you want to hard code values like here. But the tibble function is great if you want to use other variables or want to work with other functions to create the data. So for instance, here we could have also created this plot, or not this plot, this tibble in the same way by simply using the different R functions. So here I could use some calculations and I would get the same again. So basically we can create tibbles here, which is great, I guess. And so we have a toy example now. Again, with a tibble like this, we can do all of the stuff we already used to. So for instance, like the filtering function, which is also part of the dplyr package. So part of, it's not, we cannot read it anymore. So the dplyr package. This is how it's written. So as you can see, this is the package where filter is coming from. And this is also the package from where Mutate is coming from, and Summarize, which we'll later see on. So this is the data wrangling package, or the main data wrangling package in any case. So with dummies, we can use filter here. I just wanted to give another example of how filter works, because in the last, I mean, it's pretty straightforward, but in the last chapter we have done it without much explanation. So here I kind of wanted to give you a small explanation of how the code works. So for instance, filter basically takes needs to get true or false values so that it knows which values to keep, which correspond to the true values, and which values to discard, or which rows to discard, which correspond to the false values. And so basically you can work with any function that gives you back true or false values. And between is such a functions, it basically asks, checks whether a value, say, or a variable, say name2 in this case, so this column here, checks whether this is between a couple of values, say 5 or 9. And if we only execute the between part here, of course this won't work here. We'll need to get this here. So say name2 of course can only be used here within this pipe, because it will understand that name comes from dummy. But if I only want to execute it without it, it will throw an error just like this. So I hard coded it into here. And if I execute only this, you will see what you actually get is a vector full of true and false vectors, have variables or values more, and filter then takes that vector and corresponds it to the specific rows. So in this case, it will mean that the first and second row will get discarded, the third and fourth row will remain, and the fifth row will be discarded again. This is how filter basically works. So it will always take a full vector of true or false values. So here, as you can see, the resulting table will be the one consisting of the third and fourth row. All right. Another way to get to specific rows within a table. So I'm trying to that we will deal now with how to access data into a table, and once we figure that out, I will show you how to mutate specific variables. So if we want to get specific rows, say the first row, then filter is not really the function to go with, because filter wants to use conditions to filter. But here our condition is not a one on variables, but it should just be the row. So the first row or the second row. So this is why we can use the slice function. So slice dummy, and then you can simply say, okay, I want to get the first row. Or can I do this too? I want to get the first and second row. Or I want to get the first, second, and fifth row. This is basically how slice works. So I guess it's pretty straightforward. If you want, you can also throw in a vector, which will give you exactly the same. Point is, slice will understand what you mean and will give you the corresponding rows to the indices you will give here. Similarly, there are other functions. So there's slice head, and they will basically work all the same. Slice head gives you the first 3 rows in this case, but you could also say like the first 4 rows. So via this argument, n is equal to you determine how many rows you want to get. There's also slice tail, which is the same, but you get the rows from the bottom. Then there's slice max, which is a bit more interesting. I will just copy and pasting this from the lecture notes into here because I think these functions are pretty straightforward, but maybe a few words will cannot hurt. So this is why I'm copying and pasting it, and I'm simply explaining what's happening. So slice max uses in this case the variable 1 column and determines the maximum values from that. So we want to get the 2 maximum values with respect to variable 1, and in this case it's these 2. Similarly, there is this min, slice min, and if you want to get 2 random rows, you can always use slice sample. So in this case, it will always give 2 different rows each time I execute it. And yeah, so this is how you can get rows. Pretty straightforward. You can do everything through the slice function if you want to get it. Now, if you want to get columns, there are mainly two functions. One is select and the other one is pull. One thing I should mention maybe here is that all of these slice functions are from the dplyr package 2, and so they are from the tidyverse, so they work great with the pipe. So of course they have data as the first argument data as the first argument. So you can simply do stuff like this with the pipe, which can help with legibility. In any case, it simply works with the pipe. So if you want to get a specific column, say from our dummy variable, say we want to get the third column, let's just say, okay, I want to get column 3. And then I got column 3. Also, I could say I want to get variable 1 and column 3. Well, in this case, I got both. So select is pretty straightforward. Again, you could use it with a pipe, and you will get the same result. And here you may wonder, okay, if select already does everything we need, so we can get any amount of columns from that, why is there another function pull? So let's look what pull does. So if I wanted to do this here, I will get an error. Oh, actually I won't get an error. But still, it's not what I wanted to do. The point of pull is to always get one single column. I will have to figure out later on why this is happening here. What is variable 1? So basically gave column 3 as names. So what happens if I say I want to get name 2? Okay, so apparently pull works with 2 columns as well. Then it will use names as the second one, but we don't have to or use the second column that you specified as names, but of the vector. So this is a named vector. These are the values of the vector. This is the names. And of course, if you give a third vector, If you have a third one here, then there will be an error. In any case, pull is really designed, in my opinion, for getting one column. So here, if I pull variable 1, you get a vector like this. And what you can see is that it's actually a vector. For instance, if you were to select only variable 1 instead of pulling it, then you will get a tibble. So select will always, even if you only extract one column, will always give you a tibble, but pull will always give you a vector. And these are the two main differences. Another way to do this here is also via the $sign. You can simply choose columns. So in this case, I could just choose variable 1, and it would get the exact same thing. Select also has a couple of helper functions, which you can look at in the lecture notes. I think they're pretty straightforward. Basically, let's just do one helper function. For instance, if I want to choose all but the first column, again with the minus sign, I can control this, same as we did with pivot longer, because there you can also use the helper functions. Here I can say, okay, take all but variable 1. And well, this did what I wanted to do. Then with the colon, we can get consecutive rows. So for instance, I could say, okay, take columns variable 1 to name 2. If there would be more columns in between, we would take those 2. So this is how select works. And if you've already worked with R or MATLAB, for instance, then you know that you can also access data or tables like this, like you could access any matrix through a row index and through a column index. So instead, so if you want to get a specific value, we could just say, okay, from the first row and the second column, I want to get that value. And here you will say, okay, here you will see, okay, I got what I wanted to. I could also say, okay, I want to get the second and third column, or the first and second row, and so on. So this works pretty nicely. And also, this is something a bit more special with R. I don't think MATLAB uses it in a way like this. Yeah, probably not, because here, as you can see, you got a tibble back and a data frame back. And if you want to, as with pull, get a vector back, then you will need to use 2 brackets here. So for instance, if I want to get the value here of the first row and the second column, then I will need to use 2 brackets. So here you can see the difference. So this is a tibble, this is a vector, and it doesn't feel like much of a difference, but the point is some functions will react allergically if you give them a tibble, but they expect a numeric value, so a vector. So this is why you will need to be careful with that. So with tibbles, you will always get with 1 bracket a tibble, as here, and with 2 brackets a vector. This is kind of consistency features of tibble. If you've ever worked with data frames, there things can get mixed up. Just for your information, I have an example in the lecture notes, but it's not that important. One last thing, I mean, there are more examples in the lecture notes, but I think you get the idea of how you can access data. If you leave out one index, then it will R will understand it as all indices. So in this case, I want to get all rows of the second column. And yeah, that's how it works. So this is basically how we can pick out specific values from tables. Sometimes that's important, and this is why we address it here. So back to maybe more interesting things, back to the mutate function, so that we can actually change our data or run computation with our data. Mutate basically works straightforward. You simply, as we've done before, you declare a new variable name or an old one. So as here, mutate works as declaring a variable name and then equaling this to a computation you want to do. In this case, it was just a conversion of data types, but here we could do anything. So with dummy, I can send it to mutate, because mutate is of the tidyverse, and this is why it works in a pipe. As you can see, the first argument of mutate is data, so the pipe will work. And now let's just say, okay, I want to compute a fourth column, which is just the sum of variable 1 and name 2. Then it's, just declare the new variable name and then equal this to the operation you want to do. And this is where you, this is how you computed it, and this is, I believe, what you wanted to get. And also what we could do, we can do multiple computations. So here we could use a fifth column, and we can even use variables that we've used, that we've just declared right now. So we could say, okay, this should be fourth name, twice the fourth name, and then we have added another column here. Okay, so this is pretty easy. One really powerful thing you can do with, or you can combine with the mutate function, is the across function. The across function basically is something you can add on top of the mutate layer, or which works together with the mutate layer, so that you can run multiple operations, or the same operation, both works, across multiple columns. So for instance, if you wanted to convert all three of these columns, then you wouldn't have to write mutate. Okay, so maybe I will just write it out. So say we want to make all of these into factors. So variable 1 should be declared as factor, variable 1, and then I would have to kind of copy and paste everything here and then change variable 1 to name 2. Yeah. So, and then I would have to do the same thing for the third variable, which is really annoying. And if you have a lot of variables, which is also impossible to do. And there you can use the across function. So the across function asks which columns do you want to use. The default is you will use every column. Here you can also use the helper function from select again. And then it asks, okay, what functions do you want to use? So let's tell across that. So the columns, let's just convert all of them, so we don't need to specify anything. And the function should be as factor. Remember that you need to give the function names here and not the function itself, so not with the brackets here, because this won't work. Now I forgot one parentheses. So you will need to get the name. And here, as you can see by the small label here, it converted everything to factor. Of course, this is a really boring example, but it's still something you will need to do a couple of times to convert something or whatever, and to do it to multiple columns. So it's really helpful to know that you can use across to do this. So this is how mutate works, or how the syntax works. Let's talk about more a bit more challenging things, let's take a look at the following example. So here I declared a tibble via tribble, so this is how my data looks like. And you could think of, okay, I want to get the minimum of each row. So I want to get a new variable, which is called minimum. And then I always want to choose, okay, minimum of A and B here. So in this case, 1 of 3. So this should be 1. In the next row, the minimum should be the minimum of 2 and 4, which should be 2. And so on. And so you could think that, okay, maybe I will just write minimum of A and B. And if you do it, you're in for a surprise, because as you see, it's actually not doing what we just thought we are doing, because this is where specialty of R comes in, because this computation is vectorized. So what Mutate does is it takes a vector and it returns a vector. So in this case, what we gave to Mutate, or to the minimum function, was these two vectors A and B. So in that is the data 1, 2, 3 and 3, 4, 5. And minimum works in a way that is a vectorized calculation, so it combines these two vectors and gives the overall minimum back. So in this case, the overall minimum of all of these values is 1, and then Mutate gets just this one value just this one value back, and because it expects a vector back of the length of 3 in this case, it will recycle the values so to the according length. So in this case, it will get back number 1 from the minimum here, because that's the overall minimum, and then it will recycle that value to all rows so that it has a vector. So this is where things can sometimes get tricky if you forget that the calculations are always vectorized. So in this case, minimum is vectorized and Mutate is vectorized too, because it expects a vector back, and this is why it triggers this recycling. So this is where things can go wrong. So if you want to get really pairwise minima, you have to sometimes be careful that you take an appropriate function. In this case, pmin does what we want to do. So this looks now more like it, or more like what we were expecting. Okay, so let's run a small case study looking at the cars data set. So cars is a data set that comes pre-installed with R, and let's just save it as tib, and we want it as tibble. So here we converted. And what data is in here is like it's the speed of cars and their corresponding distance it took them to stop. So here in the documentation you will see exactly what I just said. So it's the speed of cars, I think it's in miles per hour, and here's the distance in feet. The distance it has taken them to stop. And what we could do now is to compare those. So first let's look at the data visually. So let's run speed against distance, and we want to get a scatter plot. Oops, not path. Get point. So this is what the data looks like. So these are the observations, and we could try to compare this to a theoretical model. So in the lecture notes, you will see that I have worked out the theoretical model of the distance it theoretically takes to stop from Wikipedia. So all of that information is from Wikipedia. So the distance it takes to stop is just can be computed like this. V is the speed in feet per second, G is the standard gravity, T is a constant, which is the perception reaction time, and mu is some friction coefficient. So the constants are defined here, and now we want to compare the observed distances to the theoretical distances. So from the speeds here, we will need to compute the theoretical values. So let's do that here. So here are the constants we need, and then we can compute the distances. So what I've done is just created a new table with the theoretical distances, which is here I've just taken the speed, the feet per second, and then I've converted it to miles per hour so that it's so that we can compare it to this column here, and then I've computed simply the model or the distance it has taken to stop from the theoretical model, so just plugging in the formula. And now this looks like this. So now we can add another add the physical model to the plot. So let us just draw a line for of these here. So here we'll need to specify that the data now comes from model tip in this layer, and then we will have miles per hours and the list of model, and let's just make this a red line. So this is how the model compares to the data. And what you often want to do if you have a model like this is to see, okay, what error do we get? So of course, as you can see, the observations are not really lying exactly on top of that red line. So for each observation, we can compute the error. So in this case, we can use Tibble to do that. Not Tibble, we can use Mutate. So in our Tibble, this is our original data, and for each we can for each observation or for each row we can compute the error. First we will need to convert the speed to feet per second, because that's the unit our formula is in. This way we will get another column with the converted speeds. So this is just the speed in feet per second. Then we could compute, as we've just done now, the distance from the model, or the distance our model delivers. And now we want to compute this column to this column. So something what is usually looked at is the squared error. So just take distance minus the distance model and square it. You will have get the square error for each observation, and sometimes you will also look at the absolute error. So instead of squaring it, you usually, or not usually, you sometimes take the absolute value of it. Okay, so here we have computed all our errors now. So we can maybe save this in a table called errors. And what we're usually interested in, of course, is some key quantities that summarize our findings, because we have a bunch of errors now. It's not really useful to look at each error separately. We need to get a summary of that. And what we can do is to simply extract the column and then take the average of it. So what we often want to do is compute the mean squared error. So it's the mean of the square errors, or the average of the square errors. So what we can do is from the errors extract the column square errors and then throw that into the mean function. So this is the mean squared error, often abbreviated MSE. Or what we could also do is the mean absolute error. It's the same thing, but for the absolute error. Here let me demonstrate how we would do it with a pipe. So here first we would pull the absolute errors, then we throw that into the mean function. That's errors. So here we would have the mean absolute error. Of course here this was like a really short pipe, so it's not really that useful, but still it helps to see that you can do it either way. These two quantities now are not really comparable, but still nevertheless they are quite common quantities and they are more used for comparing different models. So for instance, here we have compared the theoretical model. We could also say, okay, instead of using this line here, fit a straight line through here and compute the errors for this now, for this model now, and then look at the mean squared error of that and check maybe that mean squared error is smaller than the mean squared error of the previous model, and this could maybe indicate that it's a better model. But in the lecture notes, if you want to look at it, you can see that the linear model, so if you fit a straight line through here, the mean squared error is actually lower, but this doesn't mean that the model is better, because we know the theoretical model is right, because it has a quadratic part. So in the formula we know that it has a quadratic part. If you fit only a straight line through there, then there won't be a quadratic part, and so this model should be wrong, but still the mean squared error is smaller, so you have to be careful about this. But nevertheless, these quantities are usually computed to compare different models, and as we just seen now, we can easily compute this with Mutate. And I think that's a good place to stop this video. In the second part we will talk about summaries then and look at another small case study where we can use summaries better. So maybe just as a quick heads up, basically what we've computed here, the mean of something is the summary of the squared error column. So it summarizes all of these values into one value, and of course with the summarize function we can do that or the similar things with all kinds of summary statistics. So it's kind of really all-purpose summary tool for all kinds of summary statistics, and we will learn that in the next video. So see you in part 2.